Welcome everybody to Algebra 2 section 9.1, simplifying, multiplying, and dividing rational expressions. So a rational expression is a ratio of two polynomial expressions. So it's essentially two polynomials being divided. And it can be a polynomial, remember a polynomial could be one term, two terms, three terms, or more. So to simplify a rational expression, we want to follow three main steps. First step is just to factor everything that can be factored. Kind of just a general first step in these. Always look to factor. So lots of factoring in this section, in this unit. Then step 2 is going to be simplifying monomials by using exponent rules or simplifying coefficients like you would normally with dividing. And then also really in the same step, or you can consider a separate step, is to also simplify binomial factors, common binomial factors. And I'm going to change that word eliminate. I think that word eliminate gives the wrong idea of what's going on there mathematically. So I'm going to change that to the word simplify. And so I would encourage you to change that as well. Once again, I think eliminate gives the wrong idea. I will clarify that once we get into binomial factors, which won't happen until we get to example 2. But then at example 2, I will talk about it. So let's go on to number 1 here. So we have a monomial divided by a monomial. So these are technically both polynomials since they're monomials. And thus this is a rational expression since it is a ratio, the first 5 letters of the word rational. So what we're going to do here is there's no factoring that needs to be done because there's only one term on the top and one term on the bottom. Factoring only happens when there's more than one term. And so we're going to just divide or simplify. So 20 and 14 simplify by 2 to become 10 and 7. And then x's, when you have the same base or something being raised to a power and they're dividing, you subtract the exponent. So we do 6 minus 2 and get x to the 4th. And if there were more x on the bottom, then the x to the 4th would be on the bottom. If it was like x to the power 2 over x to the power 6. But because the higher exponent was on the top, we keep the x's on top because it ends up being a subtraction is a positive 4 rather than a negative 4, which would necessitate moving the base and exponent to the bottom. And we can't simplify this any further. We can't multiply 10 and x. We can't actually do x to the 4th. We can't simplify 10 and 7 anymore. So we're done. On number 2, our first step, it does need to be to factor here because the top has a binomial and so does the bottom. The bottom can't factor anymore. Looking for GCF here specifically is always a first step for factoring. And the top can though. The GCF is 6, and that leaves us with k minus 6 inside the parentheses. Now you may notice instantly here that we have 6, 6, 6, and you're like, oh, okay, well, can we reduce those instantly? Is that a thing? And the answer is no, you can't. So the instance that we could do that before was something like this, when you had like 6 plus 6k over 6. Then we could have, because we eliminated it or reduced it from all three portions of an addition or subtraction part. But that's not what's going on here. We have, actually I'm going to leave that 6 plus 6k over 6 because I'm going to go back to that in just a little bit. What technically happened here, I'm going to go back to it now actually, what technically happened in this scenario was we factored out a 6 on the top and we were left with 1 plus k over 6. We just didn't actually go through this process, but this is what technically happened behind the scenes. And so we reduced the 6 and 6 here and they both became 1. And we ended up with 1 plus k times 1, which is 1. And that's how we ended up with that scenario to where all those 6's reduced to 1's. And the reason why mathematically we were able to do this here in the light blue that I just circled is because simplifying is division, and you can only divide to undo multiplication. Dividing does not undo addition or subtraction. So once again, the reason it worked here when we did in the light blue is because we are undoing multiplication that we created, because factoring creates multiplication. And so we said, oh, we have something multiplying with 6. And we can undo that by dividing the 6 out, or simplifying the 6 out, which is division. And so the same thing here is true on this problem, which is why we had to turn it into multiplication by factoring. And so now we can't just reduce like this 6 and this 6, because even though this 6 is multiplying with something, this 6 is not multiplying with anything. It's subtracting with the k. What we can do, however, is just like we could do the 6 on the denominator, since it was the entire denominator, technically it's like multiplying by 1, as anything is. And so since it's technically multiplying with something and not adding or subtracting with something, we can reduce it. And the same thing's true with this k minus 6. Technically, it's multiplying by 1. We just never write it because anything's technically multiplied by 1. And so then we can say, oh, well, we'll reduce this k minus 6 and this k minus 6 and get 1. So you can reduce or simplify or divide out, any of those three words work interchangeably, a binomial or an entire factor or something that is being multiplied with something else. And so because k minus 6 is multiplying with something else, the 6 in the numerator, and technically an indivisible 1 in the denominator, you can end up getting just 6 on the top times 1, which is 6, and 1 on the bottom, which we don't have to write. We just get 6. And typically we don't even write this 1 there that I just erased. So most often we don't even write that there. We just say, okay, well, we can reduce a factor on the top or bottom with the entire numerator or the entire denominator because we know mentally that it's an invisible 1 multiplying with it. And so that would be the answer number 2. And that's why I don't like the word eliminate for binomial factors, is because eliminate gives us the idea that poof, it's gone, it disappeared. But in math, something eliminating means that it goes down to 0. It's gone, like, because that's truly gone is when it's 0. And these don't go and become 0, otherwise, well, that would be undefined because you're dividing by 0, and you'd have 0 divided by 0, which is also undefined. And that's not what happens here at all mathematically, which is once again why I really stay away from the word eliminate for things like this, because you're not eliminating, you're simplifying it, you're reducing it, you're dividing it. On to number 3 here, we're going to again have to look to factor. On the top, there's nothing that can be factored, no GCF of y and an 8 other than 1, and there's not like a difference of 2 squares or anything since there's 2 terms. But on the bottom, there's 3 terms. We always look for a GCF, there is none, but we can make the x for 3 terms, and you're going to be doing that a lot in this section and unit. So on the top we go negative 48 because it's a times c, and the bottom would be our b, which is positive 2. And so we say, okay, what would the sides be? I encourage you to pause the video, try and finish this factoring on your own, and then resume the video once you either are stuck and need some help or want to check how you did. And so it would be a negative and a positive here, and it'd be negative 6, positive 8. That multiply to negative 48, but add up to 2. And we can use our shortcut because it's a 1y squared. And so on the top will be y plus 8. On the bottom will be 2 factors, y minus 6 and y plus 8. And so now we can notice, oh, well, we have a y plus 8 and a y plus 8 on the top and bottom that are multiplying with something else, this top multiplying with an invisible 1, and the bottom multiplying with a very visible y minus 6. And so because we're undoing multiplication, we can divide or reduce, and those both become 1, because anything divided by itself is 1. And so on the top you have a 1 that you have to write. On the bottom you have y minus 6. Because y minus 6 times 1 is itself y minus 6, to clarify. And the reason we had to write the 1 on the top of the fraction on number 3, but we didn't have to do it on the bottom of the fraction on number 2, is because 6 divided by 1 is 6. Whereas 1 divided by y minus 6 is not the same thing as y minus 6. You have to have the 1 there, so we know the y minus 6 is on the bottom of the fraction. On to number 2 here. On number 2, we once again look to factor here. The top, even though it's 3 terms, does have a GCF, so I'm going to do that first. And give me r squared plus r, so minus r, minus 20. On the bottom, I'm going to factor out an 8, which gives me r plus 4. Now the top I can do an x still, because there's 3 terms, and I'm going to do negative 20 and negative 1 on the top and bottom, and once again, I'd encourage you to pause, try and figure this out. It ends up being negative 5, positive 4, and we can use a shortcut because it's the 1r squared. And so on the top we get 2, our GCF, then we have r minus 5 and r plus 4. And just like always, we don't care if the r minus 5 or the r plus 4 comes first. On the bottom we have 8 times the quantity of r plus 4. And so we notice we have 2 factors on the top and bottom that are r plus 4 and r plus 4, so we can reduce those and get 1. And then also the 2 and the 8 are also multiplying with something else, and we can reduce those. They have a 2 in common. So 2 becomes 1 and 8 becomes 4 as we reduce those by 2. So on the top, we just have this r minus 5. On the bottom, we just have 4. And that becomes our answer. On number 5 here, we're going to have a little bit of a tricky scenario we'll talk about. There's 2 ways you can handle it, and we'll talk about it here. So first, let's look to factor. The top, no GCF, but it is a difference of 2 squares. So how we factor it is we do one parenthesis is the square root of the first and the square root of the second, either adding or subtracting. And the other parenthesis is whatever sign or operation you didn't do in the first parenthesis. So if your first parenthesis is subtraction, your second parenthesis is addition, and vice versa. If your first parenthesis was addition, your second parenthesis is subtraction. But both start with p, since p times p is p squared. And both end with 7, because 7 times 7 is 49. And on the bottom, that doesn't factor at all. There's no GCF there, so you can call that 7 minus p. Now, personally, actually, the way I like to go about this is different than what this watch out note is about. So I'm going to explain the way I like to go about it first, and then I'm going to explain the watch out note as well, because I like to give people options here that you guys can choose from as far as what makes sense for you. So I can't currently reduce anything because I have a 7 minus p and this is a p minus 7. Those are not the same thing. What I could do though is I can make them the same thing. And how I could do that is by taking out a GCF or factoring out a GCF on the bottom of -1. That makes it so the 7 is negative and the p is positive, and I can change the order of those just fine. I just can't change the signs unless I factor out a -1. Now I have the ability to reduce p minus 7 and make those 1s. And so on the top, I end up getting p plus 7. And on the bottom, I have -1. And so I could then call this -1 times p plus 7. And that would be perfectly acceptable to leave my answer like that. Or I could distribute the -1 back in and call it negative p minus 7. Personally, I leave my answer like this because 1, it's lazier, and 2, we want everything factored for these, and so you don't have to undo the work you did to factor. You can just leave it factored. It's actually often preferable or preferred for rational expressions that you leave it in their factored form to show that you looked for factors. Now let me talk to you about the other way you would do it, and it's actually going straight from what the orange step was. So I'm going to rewrite that orange step. P minus 7, P plus 7, and 7 minus P. And this is essentially a shortcut that shortcuts past the purple to the blue. And so what ends up happening is the shortcut says, hey, A minus B and B minus A. Notice A and A, B and B, but which one is getting subtracted changes. So on the top, the B is subtracted. On the bottom, the A is subtracted. So the signs of everything flips. Well, just like if I have 5 divided by 5, it's the same thing on the top and bottom. It's like, hey, we have A and B and B. But I say, okay, now it's actually at -5 on the bottom, perhaps. So the signs flip, just like we did down here. All the signs flipped. Well, we know this ends up being -1. And the same exact thing is true down here, that this ends up being -1. Anything divided by its opposite is -1. And it's the opposite via addition or subtraction because it's the same terms with different signs. Same terms with exact opposite signs. So on the top, the A is positive, bottom it's negative. On the top, B is negative, on the bottom it's positive. So the signs just flipped. So when you divide those, you get -1. And so we could use that to shortcut from this orange step. And so we can say, oh, these match that criteria. They both have a P, they both have a 7, but the signs flip. And so we can look at that and say, oh, that reduces actually to -1. And I get -1 times P plus 7. And that shortcuts me actually even past the blue to the red. And so that's one way to go about it. And like I said, that little shortcut works anytime that you have the same terms exactly, but with the exact opposite signs. So if this was like -7 and -P, this would not have worked because the signs would not be completely opposite. They're only partially opposite because the 7's have the same sign. So once again, you have to have the exact same terms with the exact opposite signs. Now if we look at number 6 here, I do want to explain actually real quick on number 5 one more time here, that the reason I do prefer this top one personally, that's what I do, is because it doesn't rely necessarily on a shortcut, but rather it forces you to go through the math and think about mathematically what is going on here via factor. That doesn't make it better than the other method. It doesn't make the shortcut method worse. It just makes it my personal preference for what I do. But like I said, you will have your own preference between these two, and I want you to do whichever of the two you prefer. So on number 6 here, we're going to look to factor out. On the top, there's a GCF of 3a, giving us 4a squared minus 1. On the bottom, there's a GCF of 6a squared, giving me 2a plus 1. The top, we can continue factoring into a difference of two squares inside the parentheses. So this is 3a, and then in one parenthesis, 2a minus 1, and the other, 2a plus 1. Then on the bottom, we have 6a squared, and then the 2a plus 1. And lo and behold, we can reduce the 2a plus 1s into 1. We can also reduce our GCFs out in front. 3 and 6 reduced by 3 to become 1 and 2. And a squared, we subtract those exponents. Now, because there's a bigger exponent on the bottom, I'm going to have a to the first just become 1, because 1 minus 1 for the exponent is 0, and a to the second becomes a to the first, because we subtracted the exponents. And you kept the a where the bigger exponent was, which is the bottom here. And so on the top, you're just left with 2a minus 1 times a bunch of 1s. And 2a minus 1 times 1, however many times you want to do it, is still 2a minus 1. And so the parentheses aren't necessary there. They're optional. On the bottom, you're left with 2 times a to the first times 1. And 2 times a to the first times 1 is just 2a. Now, what you cannot do is say, boop, boop. I reduced them because, once again, 2a is subtracting with something. It's not multiplying with 1 or negative 1. If it was multiplying, then that's a different story. But you can't just divide to undo subtraction. Dividing only undoes multiplication. So that's actually done. On to number 7 here. Top, we're going to look to factor. There's a GCF there. The GCF is 2. So we're left with 3n squared plus 4n plus 1. And the bottom ends up being 2 times n squared minus 1. The top, we have to make the x to continue factoring. And we get 3 and 4 on the top and bottom respectively. And this ends up being positive 3, positive 1 in no particular order. And now we can't do the shortcut because it's a positive 3, not a 1. And so we have to do 3n squared plus 4n plus, it's not plus 4n rather, 3n squared plus 3n plus 1n plus 4 coming from the sides of these two x's, or the x, to get those with our middle variable n. And then we group the first two and the last two and look for GCFs. And the first two have a GCF of 3n, giving us n plus 3, or n plus 1 rather. And the last two have a GCF of just positive 1, giving us, I made a mistake here. Here's a mistake I made, I apologize. This last term in the red should have been a 1, because it is the same term that we ended our trinomial with. And so that will have a GCF of 1, leaving us with n plus 1. And the reason I knew I made a mistake there is because I knew these parentheses had to be the same for me to continue if I was doing it correctly, and they were not currently the same. I'm like, oh, so something got messed up. So now since those are the same, I can put those in one factor, and our other factor is 3n plus 1. So now I did all that work off to the side, so that way I could take all this and put the result up here and keep my main problem cleaner. And so I have the 2 out in front as a GCF, then I have 3n plus 1, and I have n plus 1. On the bottom, I still have the 2, and then the n squared minus 1 is the difference of two squares. So I get n minus 1 and n plus 1. and I look to reduce anything I can. And I can reduce an not minus 1, but I can reduce an n plus 1 on the top and bottom, and I can reduce the 2's on the top and bottom, since those are both multiplying with different things. And so this leaves me with 3n plus 1 on the top, multiplying with 1's, and n minus 1 on the bottom, multiplying with 1's. And that's my answer. I can't reduce the n's, I can't reduce the 1's, because n is not multiplying with everything on the top, and n is not multiplying with everything on the bottom. The same thing's true for 1 on the top and bottom. Going forward, you're going to see me skip this step of factoring and jump straight to this. I'm going to be expecting you to do that factoring on your own. I would encourage you on future examples to pause when I say, hey, I'm going to factor this, and I'm going to use what's called the guess and check method, but I'm going to say, hey, I'm going to factor this. I would encourage you to pause the video, work on factoring on your own, and then you're going to just see me put the factors up. And once again, if you need help factoring, not once again, but if you need help factoring, I would encourage you to go back and look at our previous sections and previous units that specifically discussed how to factor trinomials. On number 8 here, top, we have a GCF, it's 5, and that gives me 9 minus w. On the bottom, I don't have a GCF, and so I'm going to factor this, so this would be a good time to pause it. I end up getting 3w minus 1 and w minus 9. Now I notice that this top and bottom aren't the exact same, but they're similar, and so that's one where you could do the shortcut, or like I like to do, I'm going to flip-flop this one around since I like to start it with the variable, and I'm going to make it a negative 5 with w minus 9, because that'd be like a negative 1 getting factored out and multiplying with the 5, and I have 3w minus 1 and w minus 9. Now those w minus 9's are the same, and I'm left with negative 5 over 3w minus 1. And that's the exact same answer you would get if you just did it from here to here using the shortcut that we talked about earlier, and then it would be a negative 1 in its place, and negative 1 times 5 is, well, negative 5. So once again, I don't care which of those you do, I want you to do what works for you. Moving on here, we're going to talk about multiplying rational expressions. So here, there's a couple of different ways to go about the monomials, but as far as binomials or trinomials go, there's really just one way to go about it. So if you have monomials only, like you see on 9 and 10, you can choose to either multiply them together, then simplify. So I'll talk about how you would do that, and then I'll also talk about doing my preference as well. Once again, I don't care which you do, they're the same resulting at the end, and that's fine. And so here you can multiply the numerators, because when we multiply straight across. And so you get 6 times 10 is 60, x squared and x to the third gives you x to the fifth, because we add exponents. And the y's, we get y to the seventh for the same reason of adding exponents. Denominator, 2 times 18 is 36. We get an x squared with no other x's from this one. And the y squared and y squared, we add the 2's and get y to the fourth. And then from here we'd say, okay, well, now I'm going to reduce like I did on the very beginning of the section, to where 60 and 36 becomes, as I move it down here, 60 and 36 reduced by 6 to give me, actually reduced by 12 rather, even more, and give me 5 and 3. And then with my x's and y's, I'm going to subtract big minus small for exponents for x's and y's individually, and then I will keep the base and the exponent where the bigger exponent is. And so the bigger exponent is on the top for each of these. So 5 minus 2 for x is x cubed, and 7 minus 4 for y's is y cubed as well. And this is my resulting answer. Now, the way I personally prefer to do it is what you're going to see here on number 9, what I'm going to do right now. And so if I have the same starting point of the problem, I'm just going to look to vertically and cross reduce, both vertically and cross, like I mentioned. And so just like we normally do with fractions. So I'm going to look for like 6 and 18 reduced by 1 and 3, for example. You could have reduced 6 and 2. I just wanted to do 6 and 18. There's not a wrong way to go about that between those two. As long as you're doing something from the top and something from the bottom, you're okay to reduce. It just can't be 2 things from the top or 2 things from the bottom. So I could also do it with 10 and 2, reduce by 2 to become 1 and 5. And I can do the same thing with my variables. So I see x squared and x squared here. So I'm just going to reduce those, and anything divided by itself is 1. Or we subtract both exponents there as we reduce those, and 2 minus 2 is 0, so we don't have any x's left, essentially. I can do the same thing with the y's, to where I get y cubed and y squared. Y squared, we subtract 2, we don't have any y's. And y cubed, we subtract it 2, and we get y to the first. And then over here on this next fraction, the x cubed doesn't have anything to reduce with, but the y to the fourth does. And it becomes y squared, and y squared become 1, because you don't have any y's left. And so then as I look at this, I say, okay, what do I have left? I have y to the fifth, I have 5, I have y squared, and I have a 3. Oh, and I have my x cubed. And so on the top, I have the 5, which, right there. I have the x cubed, which is right here. I have y to the first and y to the second, which give me y to the third when I add those exponents. And then I have this 3 on the bottom. And so we get the same resulting answer. And the reason I prefer this, that I did in the green and blue, is because then I don't have to worry about the step of multiplying and making things bigger. I just focus on making things smaller. Now, the downfall is you can say that there's a lot more to keep track of there with all those slashes going on, and rewriting of things. And that can be hard for some people to keep track of. So if that's going to be hard for you to keep track of, then multiplying together like you see in the purple, and then go to the orange. But if that makes sense to you, what I just did there, then do the green and blue and then go to the orange. Both get you to the same answer in the orange. It's just 2 different ways. So on number 10, I'll show both ways again here. So I'll first start by multiplying them together. And so 4 times 5 is 20. On the a's, we get a to the 5th and b to the 8th. On the bottom, 15 times 12 is 180. And then we get a to the 5th and b to the 10th. And as I look to reduce this, 20 and a 180, well, the zeros, just automatically you can reduce those by 10 and get 2 over 18. And so that reduces by 2 to become 1 and 9. And I'm just going to leave the 1 on the top there. You don't necessarily have to write it always, but if there ends up being nothing else on the top, we'll need it. For a's, a to the 5th and a to the 5th give us no a's, so we just get 1 from that. And b, 8 and 10, the bigger exponent's on the bottom, so I'm going to subtract that, and it's going to leave me with no b's on the top, so I just get 1 on the top, rather. Not b to the first, but just the number 1. And b to the 10th becomes b to the second. And so I get 1 over 9b squared. So I could do the same thing over here on the original start of the problem here as well. Logan, let's not push people into posters. Yeah. Hey, don't rip her hair out. enough to overpower sometimes. What's up, Zach? What are you going to take pictures of?
The Facebook slide, assuming it happens.
Assuming it happens. Hey, day, Coach.
Hey.
You have a good day? Good. Happy to hear it. Good. So I would start by reducing vertically and diagonally. So for example, 4 and 12 reduced diagonally to 1 and 3, reducing by 4. 5 and 15 reduced by 5 to become 1 and 3 as well. And then I look at the a's here, and I say, okay, well, a squared and a to the first on the top and bottom there. A squared would become a to the first, and a would become 1 as we subtract exponents. I do a similar thing with the b's here, where b to the second become 1, and b to the third become 1. Or b to the third become b to the first. So notice I cross out the entire b here, but not the entire b there. Or you could choose to rewrite it as like b to the first there. Either way is fine. Whatever makes most sense to you. And then with the next one, next fraction, I still have an a to the first here and a to the fourth. So I'm going to reduce that. A to the first would now become 1, and a to the fourth becomes a to the third. And oh, a to the third and a to the third. Reduce those and get 1. And I'm going to put multiplication dots there so I don't confuse myself. And then I have b's. I have a b to the 6th here, and I have a b to the 7th here. So I'm just going to become b, or just 1 as I subtract all 6 of those. And this is going to become 1, b to the first. And so I have b to the first. I'm going to do this in blue. B to the first, b to the first, 3, and 3. And we see that 3 times 3 ends up giving us the 9. And then the b to the first and b to the first ends up giving us the b squared. And so we get, once again, the exact same result. Number 11 here, though, we have binomials and trinomials. So you really just have to focus on factoring first, all parts. You have to factor this numerator, this denominator, this denominator. Lots and lots of factoring. So if you were bad at factoring going into this unit, you'll probably be a lot better coming out, as long as you work hard at it, because you're going to get a lot more practice. So I'm going to factor each of these 4 parts. So I'd encourage you to pause the video, work on factoring these, and then resume the video when you want to keep trying. So this top part will factor out a 4, giving 4x rather, giving me x minus 1. The rest of this fraction, I factor out a 2 as a GCF. And then it factors further. It factors into x minus 1 and x plus 3 in no particular order. Get done the x plus 3 first. In the second fraction, the top ends up becoming x minus 2 and x plus 3. And the 4x squared plus 8x on the bottom there, I factor out a 4x, and I get x plus 2. Now I look for any common binomials on anywhere in the numerator. A numerator could be left or right, and anywhere in a denominator could be left or right. So I see an x plus 3 on the top and the bottom, so I reduce those. I see an x minus 1 on the top and bottom, so I can reduce those. And I see nothing else here, because this is a minus 2 and this is a plus 2. Okay, so those are going to stick. Those are going to stay. And then I see, okay, well, what about GCFs out there, some monomials? 4x and 4x, those link up perfectly. I could reduce 4x and 2 by 2, but I see this as being a more straightforward opportunity, so I'm going to do that. If I reduce this still, I would still get the same correct answer, to be clear. What would happen there, I'll talk about that in a moment. But here, these reduce and just become 1, and I just end up now with an x minus 2, a 2, and an x plus 2, and everything else is just a bunch of 1s multiplying, which has no consequence on the problem. If I did it the other way here, I would have had this 4 becoming a 2 and this 2 becoming 1, and then I have to now reduce this 2 and this 4, and I still end up with a 2. I have to reduce the x's as well. Now, so now I'm just left with this 2 here, and I'm going to go ahead and consider that to be the same as before, because it is, because I have this 2, this x plus 2, and this x minus 2. So I'm just going to back up and do it how I had it earlier, because once again, I think that's a lot more straightforward to have 4x and 4x reduce with each other and give us 1. And so now I have on the top x minus 2, on the bottom 2 times x plus 2, which, as I mentioned before, that we could distribute this 2 back in, but it's far from necessary, and I just prefer personally leaving it like this. But distributing that 2 back in is not wrong. Number 12, we're going to do the same thing, so I'd encourage you again just to factor as much as you can here. So I'm going to start factoring. Top left, this ends up factoring out a 5v, and I'm going to do a negative 5v, so that way my v comes first. I'm going to switch the signs around because that's what I prefer doing. And then that'd be minus 2. Otherwise, this would have factored into 5v outside and then 2 minus v. But I factored out a negative, so that way I could flip the signs there. The bottom factors into v minus 9 and v minus 2. The top right factors into v minus 9 and v plus 1. And the bottom right ends up just saying 15v, there's nothing to factor. And so now I have v minus 2 and v minus 2, which I could have had here and here anyway. But this would have divided to be negative 1, giving me negative 5v. And this divides to give me positive 1 with still a negative 5v. So it stays the same regardless. I see a v minus 9 on top and bottom here that I can reduce. Nothing to reduce the v plus 1 with, so I'm going to have that still. But I can reduce this 5v with the 15v. So negative 5v will become negative 1 as I reduce it by 5v. And 15v, as I reduce that by 5v, becomes 3. And so at the end of all of this, I get v plus 1 on the top over 3. Or sorry, negative, parentheses, v plus 1 over 3, because I have this negative 1 still I have to worry about. And if you want to distribute that negative in and call it negative v minus 1, be my guest. If you don't, be my guest. Now we're going to move on to number 13 here, dividing rational expressions. So we have a division symbol here instead of multiplication symbol. Well, we learned before that when you divide fractions, all you do is multiply by the reciprocal. What's a reciprocal? Well, thanks for asking. It is the flipped version of the fraction. Now you only flip the second fraction. You only have the reciprocal of the second fraction. So we're going to turn this division into multiplication. And so it becomes 5pq over 16p cubed. Nothing changed. Q and cubed might get confusing, so I'm going to call it q and p to the third power. And the second fraction, we flip it. So it becomes 8q to the power of 5, 35p squared, q squared. Now we handle this the exact same way as we did above. So you could either multiply these numerators together, multiply the denominators together, or go through and look to cross reduce. Either way is the exact same. So if I multiply them together, for example, I would get 40p q to the 6 over 560 p to the 5th q squared. And as I look to reduce this, slashing out these zeros, dividing by 10 helps a lot there. And I have 4 divided by 56, which ends up being 1 and 14. So I'm going to have a 14 on the bottom. And a 1 you could write on the top, but we might not need to. Then the p's, p, we subtract the next one of 1. Just get 1, not a p to the first, but just a 1. And p to the 5th subtracts by 1 and gets p to the 4th. So I'm going to have a p to the 4th on the bottom. And with my q's, the bigger exponent's on top, so 6 minus 2 gives me q to the 4th. And this becomes a 1 on the bottom. So I get q to the 4th, or 1q to the 4th, over 14p to the 4th. And even though these are the same exponent, there's nothing we can do there since they're different variables. Now, as I mentioned before, I personally like to cross-reduce in the purple step and to use that to get to the orange. So if doing that, 5 and 35 would reduce by 5 to become 1 and 7. 8 and 16 reduced by 8 to become 1 and 2. Then we have the p's. P and p cubed end up becoming, again, 1 and p squared. Q and q squared ended up becoming 1 and q to the first. And then we have q to the first and q to the fifth vertically here. And that will subtract to give me q to the fourth and 1. And so now I still have my q to the fourth on top. Still have the option to write a 1 there. I have 2 times 7 giving me 14. And I have p squared and p squared giving me p to the fourth on the bottom. So regardless of whether you go with the blue, cross-reducing and vertically reducing, or the green, then to the orange, it gets the same result regardless. On to number 14 here. Again, we have division. So again, we're going to multiply by the reciprocal. So the first fraction remains unchanged. You could start factoring in this step if you want to. I often do myself. And then we flip the next fraction, giving us x squared plus x minus 6 over 2x squared plus 6x. So you could feel free on that step to be clear to have written the factored form of this, this, and this instead of the unfactored form. But now I'm going to factor, so this is the opportunity to pause the video. So on the top left, it just stays 10. There's nothing to factor because there's only one term. Bottom left, we can factor out a 4, giving us x minus 2. Top right, we make the x, and we end up getting x minus 2 and x plus 3. And on the bottom right, we have a GCF of 2x, giving us x plus 3. So now as I look to reduce vertically, diagonally, you name it, I have an x minus 2 on the top and bottom here. I have an x plus 3 on the top and bottom here. And then I have this 10 that I can reduce with either the 4 or the 2. It really doesn't matter. So I'm just going to do the 4, I suppose, and reduce that by 2 to become 5 and 2. And so now on the top, I just have 5. Well, that kind of wigged out there. And the bottom, I have 2 times 2x, which is 4x. And man, I find these incredibly satisfying to know that we went from all of this, and we got it down to just to 5 over 4x. I think that's pretty cool. But I'm also a math teacher, so, take that with a grain of salt, I suppose. Number 15 here, again, we'll just start by flipping that second fraction and turning it into multiplication. And if you wanted to, instead of writing the unfactored version here like I am in the purple, you could write the factored version of everything. So as I flip the second fraction, a squared minus 8a plus 15 is on the top, and 24a squared minus 8a cubed is on the bottom. And so now I'm going to look to factor here, so here's your heads up. Top left ends up factoring out a 2a squared and giving me a minus 6. Bottom left, to be clear, the a minus 6 doesn't factor in the top left anymore because it's not a difference of two squares. Neither of them are squared, are perfect squares. Bottom left, this factors into a minus 6 and a plus 2 utilizing the x and the shortcut. Top right, once again, utilizing the x and the shortcut, I get a minus 5 and a minus 3 in no particular order. Bottom right, just a GCF again, I have 8a squared as my GCF, and I have 3 minus a there. But I'm going to turn that 3 minus a into a negative 8a squared and doing a minus 3, because I always like my variable leading it, and that way these match. But once again, you could have just divided those and had the result be a negative 1 like we talked about in our shortcut earlier. So now as I actually look to reduce, I see a minus 6 and a minus 6 are the same. There's nothing with a plus 2, so I'm going to leave that. A minus 3 and a minus 3 are the same. There's nothing with a minus 5, so I'm going to leave that. And then 2a squared and negative 8a squared. The a squareds reduce to 1, and the 2 and 8 reduce by 2 to become 1 and negative 4. And so my answer to all of this is a minus 5 all over negative 4 times a plus 2. And if you reduced this earlier and called that a negative 1 instead of factoring out a 4, factoring out a negative 1 and calling that a positive 8a squared, then you might have your negative on the top and a positive 4 on the bottom. And that's the exact same answer, to be clear. And you could even choose to distribute this -1 and call it -a plus 5. That would still be the exact same answer. So just to be clear, I'm not concerned about where the negative is on the top or bottom of a fraction or just out in front of a fraction. Regardless, the fraction here is negative with that 4 out in front on the bottom. Moving on to our last problem for the lesson, number 16. Oh, we got 3 fractions here. So this first fraction will remain unchanged because it's the first fraction, to be clear, and you never change that one for flipping it around. The second fraction, we're dividing it, so we're going to flip it. It's technically over 1, so it's going to be 1 over 4k plus 1. And now the third fraction, since it's being multiplied, will not flip. Now if there's another division symbol here, then this would flip too, to be clear. But that's not what's going on. So this stays 16k squared minus 1 over k plus 3. And now I'm going to look to factor if you haven't already. So the top left doesn't factor, the bottom right doesn't factor, the top middle doesn't factor, the bottom middle doesn't factor, but the top right does, into 4k minus 1 and 4k plus 1 based upon using a difference of 2 squares. And the bottom right doesn't factor either. So now this is fully factored, and I'm going to look to reduce anything on a top of a fraction with anything on a bottom of a fraction. So I could go within the same fraction, I can go from 2 separate fractions. It doesn't matter which fractions I go from, as long as it's on the top of one fraction, and as long as it's on the bottom of another fraction, I can reduce them. So for example, k plus 3 and k plus 3 reduce, 4k plus 1 and 4k plus 1 reduce. But this k does not reduce with this k, because that's not only just a k, it's a 4k minus 1. So on the top, I'm left with 4k minus 1. On the bottom, I'm just left with k. And that's my answer. And that will close out Unit 9, Section 1 of Algebra 2.